before we do example 3, I want you guys to recall our math review. So this is the first page in your notes, and this part's going to be a little important. But what kind of relationship is this? It's a directly proportional, and if I double x, what's going to happen to y? It will also double. Now, we're going to use a new notation today. We're just going to say there's some new y prime, right? And I say, hey, if I double x, what happens to y? We're going to say I'm going to get double the y that I started with. You guys see that? Okay. What would happen if I triple it? It would triple. What kind of relationship is this guy? It's inversely proportional. So if I doubled x here, my new y would be, it would be half as much. If I double the x, I'm going to have half of the y that I started with. You see? So my new y is going to be half as much. So this is kind of the notation that we're looking at. That y prime is a nice way to kind of organize to say how you are multiplying your original amount, right? What kind of relationship is this? It's also direct, but how is it different from this direct relationship? Right? So it's curved. So if I doubled x here, what would happen to y? Yeah, how much greater would y be, though? How many times greater? Yeah, 2 squared, which is 4. So if I tripled the x, what would happen to y? It would be 9 times greater, right? So my new y prime for this guy, if I tripled it, then I would have 9 times more than the original y I started with. Is everybody okay with that? Yeah? What about if I put something new? Because we can have all types of relationships. What if y is proportional to the square root of x? Yeah, so like if we looked at the graph, it would look like a sideways, the top of the sideways parabola, right? So what if I have x, what if my x is 16 times greater? What would my y prime be in comparison? It would be 4 times the y I had. Does that make sense? Everybody's okay with that? What if I only tripled my x? So my y prime would be root 3 times the y that I had. Make sense? Just like it was when I did 16, it was really root 16 times y, but root 16 was 4y. Okay, so that's a little bit of review, and that's going to take us right into where we're going. So we have a cart, and it begins from rest at a time t equals 0. What does that mean, begins from rest? The initial velocity is 0 meters per second. It starts from the top of a long incline, and it's going to roll down with constant acceleration. What does that mean about my acceleration? It's constant. It's not changing. So A is constant. At this final time t, the cart has rolled a distance d from its starting point. So we have time of t, and we have a distance d from its starting point. So that is my position from its starting point is going to be d. But we want to know how far the cart has rolled at a time of 5t. Okay? So when I look at this, I have constant acceleration. What should you be thinking about anytime you hear those words, constant acceleration? Your kinematic equations. So we take a look at this. These are all constant acceleration, your kinematic equations here. So when I'm looking at this, if I have v naught, a, t, and delta x, which one of these satisfies using all these variables? The first, the second, or the third? We have x, t, a, and initial velocity. That would be the second one. Here's my initial velocity. This is my delta x. Remember, I would subtract this, so this is delta x. There's acceleration in time. So we're going to use delta x equals v naught t plus 1/2 a t squared. But what is my initial velocity, you guys? That's 0. So what I'm going to do, you're going to see me use this notation a lot. I'm just going to show that that's 0. Okay. What is delta x for my problem here? It's d. equals 1/2 a, and my time is big T. Good so far? Okay. What is constant in here? Acceleration, and the time's going to change depending on how far it goes. The 1/2, right? The 1/2 doesn't change either. Make sense? So this is my constant. So my constant K. So that's the piece that's not changing. And therefore, what is D proportional to? To time squared. So here's my question to you then. If my time is 5 times greater, what is my new distance in comparison? It's going to be 25 times the original distance. Okay, yeah.
So you have T, and so you have initial velocity times plus acceleration times time squared. Why isn't that also 0?
Because only my initial velocity was 0, but I have acceleration. So this is canceled out. So this would be like delta x equals 0 times t. So that's why it's canceling out. So we don't have to worry about that part.
I thought t was 0.
Oh, the initial one would, but for this time, it would be the total time from when you start. Yep, great question. All right, so this is one way to do it. This is my preferred method. My personal preferred method. That's not the case for everybody. I am going to show you guys a different way. And my goal is I want to find a new D. Let me use this color here. I want to find this new D, right? So I'm looking for D prime, and I'm going to take this equation, and I'm going to have 1/2 A times T. Only I need a 5T here, sorry. So I'm going to squeeze in a 5. 5T squared. Did you guys see that? So my new distance, I'm plugging it into this equation, and I'm putting 5T in there. And I'm going to divide that, because what happens is if I find the ratio of the distances, that will eventually give me a comparison of the two. So I'm going to set up a proportion. So my other D was 1/2 A times squared. So here's my new D divided by my old D. Why does that matter? Because if I took my new D over here divided by this D, I would get 25. Do you see what I mean? So I'm trying to find that number comparison. All right, so coming over here, the 1/2 cancel out, and the A's cancel out, the acceleration. But what is 5T quantity squared? 25T squared divided by T squared. And now what else cancels out? T squared. So notice my ratio of D prime to D is 25, and if I multiply both sides by D, then what do I get for D prime? 25D. So this is another way to set up to get that same ratio. So if you're looking for how much you're increasing the distance by, just do a ratio of your new distance to your old distance. Make sense? Okay. So the next problem. This one's a little bit different, so I'm going to walk you through this. We have two objects, A and B, and they are accelerating from rest. Why is that part important? So we know the initial velocity is 0 meters per second. We know again that we have constant acceleration. Okay, now object A, you guys, it accelerates for 9 times the distance as object B. Okay, so it has 9 times the distance that object B has. How much faster is object A moving than object B? All right, so if that's the case, if I'm looking at the displacement for A, right, that is going to be equal to 9 times the displacement for object B. Make sense? So that's this sentence. It's 9 times the distance. Good? So we know that relationship. And then what are we looking for? What are we looking for? I heard somebody mumble it. The final velocity. So we're trying to compare those final velocities. All right? So we're comparing the final velocity of A to the final velocity of B. That's what we're comparing. So we have two ways. We can set up a proportion. So we got to figure out we need to first figure out the equation that works for both, and we can set up a proportion this way, or we can also do it this way. I'm going to set it up this way just so you guys can see that first. Okay, so let's talk about the equation we're going to use. We want the final velocity, right? And we have acceleration, we have displacement, and we have initial velocity. Of the three kinematics, which one is going to be best represented? Yeah, I would say the third one as well. Yep. So the third one, because there's no time, we don't want to use the first one or the second one because there's no time for us to represent that with. So that equation is v squared equals v naught squared plus 2a delta x. But what do we know about our initial velocity? We know that's 0. So now I have this v squared equals 2a delta x, okay? Now, if I were doing this, I like to set up the proportion, right? And I would want to first eliminate my constant. What would be my constant in here? Yeah, so this is not changing. That's my constant. So I would get v squared is proportional to delta x. However, I would want to rewrite that because I want to really look at the velocity, right? So what would v, the final velocity, really be proportional to? The square root of delta x. Makes sense? So when I look at this, I'm like, oh, this is my relationship, right? So if I'm trying to figure out how much faster A is than B, I'm like, well, what am I doing to B that's different from A? I have 9 times as much distance in comparison. So if that's the case, then how much more velocity am I going to have? So VA is going to be 3 times more the final velocity than B because my displacement is 9 times greater. So that is how I like to do it. But let's set up the proportion. So VA over VB equals, well, VA, I'm going back to this equation here. So we can do squareds in here. We'll go back to the squared, and I get 2 times A, and then it's going to be times 9 delta XB. And then VB, I have V squared is 2 times A times delta XB. So what cancels out here? The 2 A's and the delta XB's. So I really get VA squared over VB squared equals 9, which means V sub A there squared equals 9 VB squared. And now what do we need to do to both sides? Take the square root. So VA equals 3 times VB. 2 ways, same problem.